Right, now we've remembered about what groups are, let's do some basic theory about groups. 4.2 basic theory. So remember, the order of an element of a group is the smallest n you can find such that g to the n is the identity. So let's work out some orders of groups. What's the order, orders of elements, I mean. What's the order of, we're going to take a rotation by an angle of 2 pi by 3 in O2, which is the group of symmetries of a circle. And what's the order of that? Well, of course, it's 3 because you've got your circle, right, and you go around 2 pi by 3, and if you do it again, you'll go around another 2 pi by 3, and if you do it again, you'll go around another 2 pi by 3. 1, 2, 3, you get back to the beginning again, which is the identity. So what about rotation by 2 pi by n? Well, that's going to be n, right? Because you go around n times and you get back to the beginning again. What about reflection through alpha for any alpha? The order of that is going to be 2. Because you only have to do it twice. You do a reflection one time and you do a reflection another time, you definitely get back to where you started again. So 2 is the smallest number of times you need to do it to get back to where you started. Okay, the second lot of examples. What's the order of a cubed in C12? C12 here is going to be generated by A. So it's got elements 1a, a squared, a cubed, a4, and so on. So how many times do you have to multiply a cubed by itself until you get back to the beginning again? Well, the answer is obviously 4, because we've got a to the 5, a to the 6, a to the 7, and so on. So a cubed, if we do that twice, we get a to the 6. If we do it 3 times, we get a to the 9. And if we do it 4 times, we get a to the 12, which is the same as 1. So we did it, that's 1 time. 1, 2, 3, 4. Now, slightly more interesting is what's the order of a to the 4 in C6? Well, here we can imagine ourselves going around a clock, I suppose. Let's see if I can draw a 6-hour clock. 1, 2, 3, 4, 5. So we do a to the 4. So we could have written this as 1a, a squared, a cubed, a to the 4, a to the 5, I suppose. So we're going to start with, we're going to go around to a4, that's 1, and then we're going to go 1, 2, 3, 4 again, so that's 2, and then we're going to go 1, 2, 3, 4, so that's 3, and oh look, we've got back to the beginning again. So the answer to that was 3, because let's do it on this slightly clearer clock. I'm going to go once round by 4, that's 1. And then I'm going to go another time round by 4, 1, 2, 3, 4. That takes me to 2. And then I'm going to go 1, 2, 3, 4, and that gets me back to the beginning again. So I went 3 times and I got back to the beginning again. So what's the general answer for AM in C to the n? Cn, the cyclic group of order n. Well, the answer in this case, it's a little bit harder to work out, but you think with your brain. Think with your brain, you'll be able to work it out. What you have to do is you have to keep going. You have to keep going up multiples of m until you get to a multiple of n, right? And what's the least number of times you have to go up multiples of m in order to hit a multiple of n? Well, which multiple of n is going to be the first one you hit? The first one you hit is going to be the lowest common multiple of m and n, right? That's the first one you hit, but how many times did you have to do m to get there? And the answer is, you divide that by m, you'll find out how many times you had to do m to get there. And so the answer is the lowest common multiple of m and n divided by m, but here's the slightly tricksy point. Remember the relationship between the lowest common multiple and the highest common factor. The lowest common multiple times the highest common factor is m times n. So the lowest common multiple over m is the same as n divided by the highest common factor. So we could also write this as n divided by the highest common factor of m and n, which might be easier to work out in actual examples. Right, and now let's look at the last example with cyclic subgroups. Every element G of a group generates a cyclic subgroup, and this is called G, and that line's a bit wonky, isn't it? Oh well. And what's the order of that group? Well, what it's going to have in it is all the elements up to G to the n minus 1, because if you go any further than G to the n minus 1, the order of this element is n, right? If the order of this element, if the order of G equals n, then that's as far as you need to go in this cyclic subgroup, because if you go any further, G to the n will actually equal 1 and you'll just get back to where you started. Moreover, all the elements up to G to the n minus 1 will be different. You won't hit, because you won't hit 1 any earlier, because n is the smallest number such that G to the power of n equals 1. So if the order of the element G equals n, then the order of the subgroup generated by G is also n. So this is where the order of a group and the order of an element actually come together, which is either more or less confusing, depending how you feel. Right. So the next thing is about cosets. Everybody loves cosets. If we take a subgroup of a group, the left coset, so we take H, a subgroup of G, the left coset, AH, is what you get if you take all the elements of H and you go around multiplying them all by A on the left. So it's all the elements AH such that H is in H. So you imagine you've got your subgroup here with its elements in it, and you've got your A, and you go around hitting each element with your A in turn, and you see what happens. And that's what your coset is. And there's a right coset as well. And then we've got the question, can we have AH equals BH apart from if A equals B? So if A doesn't equal B, can the cosets be the same? And the answer is yes! That's practically the entire point of cosets. The answer is yes. This is practically the entire point of cosets. And when is it that they're the same? I'm going to start over here because this is so important. This is so important. I'm going to say it again. This is so important to remember when it is that cosets can be the same. When are cosets the same? Very important. When does AH equal BH? Well, what would it have to mean? It means that when you go around multiplying all your elements by A, you get some set. When you go around multiplying all your elements by B, you've got to get the same set. It doesn't mean that each A little h is the same as B little h, but it means that each A little h has to be B some other little h. And so what this means is that A, the little element A, certainly has to be inside the coset BH, right? You've got your subgroup H. There's definitely an identity element in here somewhere. So when you go around hitting it, when you go around hitting every element by A, you'll definitely get an A, okay? So we definitely have A in the coset AH. So if AH equals BH, you've definitely got to have little a in BH, but that turns out to be enough. And this is exactly the same as saying that there exists some little h in there such that A equals BH. And this is exactly the same as saying that B inverse A is in H. We just take that B over there. And this is something that's really important to remember about when cosets can be the same or not. We will do that again later, but that's something important to bear in mind, even though we're going to do it again later. So for example, if H is the subgroup generated by A squared as a subgroup of C6, and C6 is generated by A, so it consists of A squared, A cubed, A to the 4 and A to the 5, and the identity, then what's AH the same as? Well, what's it going to have in it? Let's see what A squared is first. What is this subgroup generated by A squared? It's definitely got a 1, and it's got an A squared, and then we take our generator and we multiply it by itself repeatedly until we get back to the beginning again. So we multiply A squared by itself, we'll get A to the 4. If we multiply that by A squared, we get A to the 6. Oh look, that's the same as the identity. And so that's the end of our subgroup, okay? So that's what H is. So now if we do AH, we go around multiplying each of these by A. Multiply that one by A, multiply this one by A, and multiply that one by A. And so we can see which coset this is the same as. It's the same as this coset, and it's got an A cubed in it, so that means it's definitely the same as the coset A cubed H, but it's also got an A to the 5 in it, so it's definitely the same as the coset A to the 5H. Right. What about left cosets equaling right cosets? Do we have AH equals HA in general? The answer is no, not necessarily, but it can be true. We can have the left cosets equaling the right cosets, and if so, that's called a normal subgroup. If AH equals HA for all elements A in the group, H is called a normal subgroup. So let's have a look at an example. Example 4.2.4, we've got G is the group of permutations of 3 elements, and H is the even permutations, which is a subgroup of that. How many left cosets are there? Well, what you do is you think about how many elements the group has, and remember that all the cosets have the same number of elements as the subgroup. So you've got your big group, and you've got your subgroup that has some number of elements. And all the cosets are going to have exactly the same number of elements. So you just divide it. Take the number of elements in the group, divide it by the number of elements in the coset. And in this case, we know that this subgroup has exactly half of the elements of this. And so the answer is 2. So here are some important points about cosets. Definitely every coset has the same number of elements as the subgroup. So in fact, all cosets have the same number of elements. Then, this is at the top of page 60, every element is in a coset at least because it's definitely in its own coset, as I wrote over here somewhere. A is definitely in AH, G is definitely in GH. And A is in BH if and only if their cosets are the same. So, if we've got a finite group, then the cosets partition G into sets of equal sizes. And that gives us Lagrange's theorem. Remember Lagrange's theorem? Which says that the size of a subgroup definitely divides the size of the group. And so we get this corollary, which is that given any element of the group, the order of the element divides the order of the group. Because the order of the element is the same as the order of the subgroup generated by it. So if you take some element, remember the order of G in G is the same as the order of the subgroup generated by G. And we know that this one divides the order of G by Lagrange's theorem. So the order of the little element G must also divide the order of the group. Right, so now we can deduce this important corollary, which is that if, important corollary 4.2.6, which is, oh no, 4.2.7, if G is prime, G must be cyclic. So why is this true? Well, if G is prime, then if we pick any element of the group G, which isn't the identity, we can pick G not equal to the identity in G, right? Then it must mean the order of G divides the order of the group by that, right? But if the order of G divides the order of the group and the order of the group is prime, P prime, then it can only be 1 or P. And it's not 1 because it's not the identity. So it must be P. So the order of the element G equals P. But what does that mean? That means that G generates the group. What does it mean for a group to be cyclic? If a group has n elements, it's cyclic if there's some element G of order n. And here we've got a group of order P, and we've found an element G of order P. So that means that G generates the group. So G, little g, generates the group big G. Right. So now we've got the definition of the index of a subgroup. The index of H in G is the number of elements of G divided by the number of elements of H if everything is finite. If they're not finite, the actual better definition of index is the number of cosets. The number of cosets. Because you can still still count the number of cosets. If G is infinite and H is infinite, then you don't really know how to do this, but you can still count the number of cosets. That's going to be a little bit more advanced than we need to do, but I'll put it in there because I'm sure some of you will be interested. So here's the next thing that we have to remember, group actions. Remember that what's a group action? If you take a set, a group can act on the set somehow by moving elements of a set to other elements. And as long as that movement interacts properly with the operation of the group, then it's called a group action. So that's the definition 4.2.9. A group action on a set X says you've got a function which, for all G in the group, takes some element of the set X and returns some other element that you might write G star X. And it has to interact properly with the group structure. Those two axioms are at the top of page 61. So, for example, D4 acts on the vertices of a square because if you number the vertices of the square 1, 2, 3 and 4, every symmetry of this square will move the vertices to some other vertices. So for example, if I do the reflection in here, then 1 will go to 4 and 4 will go to 1, 2 will go to 3 and 3 will go to 2, and so D4 acts on the vertices. It also acts on the edges. If I label the edges E1, E2, that's not very sensible, is it? Do it the other way around. E1, E2, E3, E4, then every symmetry of the square moves an edge to another edge. So also E1 will go to E3 according to this reflection in this line, and E2 will stay in the same place and E4 will stay in the same place. That's another group action. Now, do you remember the orbit and the stabiliser? The Orbit-Stabiliser theorem? The orbit is everywhere that an element can go. So, for example, 1, where can 1 go? I think we've got this example down the page a bit. What's the orbit of 1 according to this action of D4? Well, can 1 go to 2? Yes, it can, because you've got a rotation. 1 can also go to 3 by a rotation. 1 can also go to 4 by a rotation. So the orbit of 1 is everything. The orbit here of 1 is 1, 2, 3 and 4, because we can get everything. And then there's the stabiliser. Remember, the stabiliser here in definition 4.2.11 means every element G that keeps X in the same place. So it's every element that fixes 1 in this case. So what are the symmetries that fix 1? Well, what could you do to fix 1? You can't do a rotation, so it's not going to be any rotations. Definitely the identity is going to be in there. The identity is always going to fix everything. But what about a reflection? Which reflection will fix 1? It's going to be the reflection in that diagonal, like that. So it's going to be the reflection. I'm going to call this reflection 1, 3, because it's reflection in the diagonal 1, 3. 1, 3, because I can't be bothered to work out what the angle would have to be of that reflection. Right, the stabiliser, note that the stabiliser of X is a subgroup. It's not just a subset, it's a subgroup of G. And the orbit of an element X is a subset of x, because the orbit of an element of x is a bunch of elements of x where you can land, right? Whereas the stabilizer is a bunch of elements of G that keep you in the same place, okay? So one of them is a subset of X and the other one is a subgroup of G. And the orbit of X, let's look at the orbit of X. Here are all the things in the orbit of X. Now, the orbit of 2 has got to be the same as the orbit of 1 because they're both in the same kind of network of places where you can go. And so this means that we've got an equivalence relation. So the orbit, that's the last thing of part of definition 4.2.11, before theorem 4.2.12, the orbit of X equals the orbit of Y if and only if X is in the orbit of Y. And so we get an equivalence relation out. And then we get our favourite Orbit-Stabiliser theorem, which says that the orbit, the number of elements in the orbit multiplied by the number of elements in the stabilizer is the number of elements of G if G is finite. There is an infinite version of this theorem, and if you're interested, and some of you are interested, then you might be interested in this. The infinite version works like the infinite version of index. It involves cosets. But we're not going to do that right now. Because what we're going to do, oh, I've actually said that on the other page, I didn't notice that on page 62. There's a more delicate version which also works for infinite groups. Right. Finally, in this revision section, we need to remind ourselves what a group homomorphism is. A group homomorphism, remember, is something from G to H that respects the group operation. So what that means is that for all x and y in the group, we could either multiply x and y together and then apply theta, or we could do theta to x and do theta to y separately, and those two would have to be the same. So it's just like a ring homomorphism we did briefly before, except we've only got one operation to think about. So you think about multiplying the elements before or multiplying the elements after you've done theta to them. And note that it follows that theta of E, it follows automatically that theta of E has to be E, so theta has to preserve the identity, and theta of an inverse has to be the inverse of what theta did originally. Right, I think that we've just got time to do group isomorphisms. So what's a group isomorphism? A group isomorphism is where you've got something going that way and you've got something coming back again that inverts it. It's like an invertible function that happens to be a group homomorphism as well. So a group isomorphism is a bijective homomorphism, and the alternative definition is that you have an inverse. So you've got theta going that way, and then you've also got phi coming back again, and they're inverses of each other. So phi composed with theta is the identity on H, and also theta composed with phi is the identity on G. Right, I reckon that's just about all we've got time for. So to make sure everybody's been following, we'll start the next lecture with a little bit of discussion about some examples of group homomorphisms.